Hey everybody, today we're going to talk about determining the polarity of covalent compounds. And covalent compounds, of course, are compounds that contain two or more nonmetals bonded together, and those bonds consist of shared electrons between the nonmetals. And when we talk about determining the polarity, we have a multi-step process that is required to make that decision. But regardless of the type of molecule we have, the starting point of that process is to determine the Lewis dot structure for the molecule first. So let's just start with an example. Let's say methane, CH4, and we'll draw its dot structure over here. And it's a pretty simple structure with carbon singly bonded to 4 hydrogens. Why is the dot structure important? Well, you note that the first question we have to answer in our process here is, does the substance contain any polar bonds? The Lewis structure helps us answer that question because it tells us which atoms are connected to each other. In this case, we simply have carbon connected to hydrogen. And since we know that carbon-hydrogen bonds are nonpolar, we can answer this question by saying no. And it turns out that if the molecule only has nonpolar bonds, then we've hit easy street because what we have is a nonpolar molecule. So methane is nonpolar, which I'll indicate here by writing NP and circling it. Now, of course, methane's not the only molecule in the world. There are many other molecules which contain polar bonds. So let's continue our journey and look at a second example. In this case, XeF4, Xenon Tetrafluoride. And let's draw the dot structure for that. So xenon's going to go in the middle, and we're going to have 4 fluorines. So we'll kind of put one on each corner here. That seems logical. And, of course, each fluorine surrounded by 6 lone pair electrons. And then if you count up the total number of electrons, there are 2 additional lone pairs that go on the xenon. So we have the Lewis structure for xenon tetrafluoride, and which clearly shows that a xenon atom is bonded to a fluorine atom, and the xenon-fluorine bond, fluorine being one of the most electronegative elements on the periodic table, is a polar bond. So in this case, yes, we have polar bonds. Which takes us to a second question, and that is the molecule symmetric? Now, Lewis structures are two-dimensional. When we ask about the symmetry of a molecule, we really are asking about its symmetry in 3-dimensional space. So we want to modify our Lewis structures to, as closely as possible, mirror the actual molecular shape of the molecule. The best way to do that is to draw what we call the projection sketch for the molecule. So let me draw that here quickly for xenon tetrafluoride. The top 2 fluorines are thought to be going into the plane of the screen, and we use these dashes to indicate that as a convention in chemistry. The bottom 2 fluorines are thought to be coming out of the screen at us, and so we use these solid wedges to demonstrate that. We fill in not very neatly again, apparently, the extraneous lone pairs, 2 on the xenon, and 3 lone pairs on each fluorine. Take me just a second here to get this correct. And we can use this projection sketch to better determine the symmetry of a molecule. And to facilitate that, I'm going to go ahead here and change my pen color to black, because what we really mean by symmetry is, can we pass a line through the center of the molecule, in this case through the xenon, and on both sides of the line, is the molecule in fact the same? So let me do that. Let's draw a line here through the center vertically. and look, and the left and the right look the same. So right now I'd answer yes, it's symmetric. Let's try a different angle. Let's go horizontally this time through the xenon. And is the molecule the same above and below? And again, the answer is yes. We could try a number of different options. Let's try one more. Let's go diagonally along the axis here and ask again, above and below, is the molecule the same? And the answer again is yes. And if the answer is always yes, no matter how you draw one of those lines, and usually doing 2 or 3 will give you a pretty good sense. If the answer is always yes, then we say that the molecule is symmetric. And if the molecule is symmetric, then the molecule, even though it has polar bonds, is said to be a non-polar molecule. So again, for the second time, both in methane and now in xenon tetrafluoride, we hit non-polar molecules. Well, certainly there must be a polar molecule out there somewhere. Let's try one more example, and that is ammonia Nh3. And so the dot structure for ammonia has a lone pair of electrons on the nitrogen and 3 hydrogens singly bonded to it. And because of that, the nitrogen-hydrogen bond is, in fact, polar. And so we arrive again at the symmetry question. Is the molecule symmetric? And again, the Lewis structure is inadequate. We want to draw the projection sketch to see if we have symmetry. So I'll go down over here in the corner and sort of redraw this here. Now in the projection sketch here, for a ammonia molecule which is trigonal pyramidal, one of the hydrogens, in this case the one on the left, the nitrogen and the lone pair are in the same plane. The center hydrogen is actually said to be sort of coming out at us, or coming out of the plane of the screen, and the right hydrogen is actually traveling back into the plane of the screen, so we use the dashed lines there for that. The center of the molecule is again the nitrogen, and so again we're going to ask the symmetry question. So let's start by drawing a horizontal line through the nitrogen. I'll use red here for the line this time. And you note that above and below the line, the molecule does not look the same. And therefore, we can conclude that, in fact, the molecule is not symmetric and therefore is a polar molecule. So ammonia Nh3 is the lone polar example we have on our screen so far. And it turns out that getting to the polar molecule means you have to go all the way through this process. Now, there are a couple of tricks to the trade to make that a little bit more efficient, okay? And that first one of those tricks to the trade is that if you have a molecule where all of or some of the exterior or terminal atoms are different, that is typically a polar molecule. An additional trick to the trade is that if the central atom contains lone pairs, the molecule is typically polar. Now, there are a couple exceptions, and actually we've seen one of those today. We drew one in Xenon Tetrafluoride. That is a molecule that has 6 electron groups around the center atom and 2 lone pairs. And it turns out that that geometry is square planar. And as we validated earlier, that is a symmetric geometry, and the molecule there is nonpolar. The other scenario is a molecule that has lone pairs, is one where it has 5 electron groups around the center atom, and 3 of those are lone pairs. And that ends up being a linear type molecule. We didn't look at an example of this one, but that one is also nonpolar. So the lone pair is not a dead cell, but it is a pretty good indication that you might have a polar molecule. In reality, this process takes time and practice to master, so you should try to apply this to several different molecules until you become comfortable with the process, so much so that you don't really need to write down the steps, and rather you can just do them for every molecule that you are handed. I hope you found this helpful, and I do look forward to interacting with you regarding future chemistry videos.